So for this lecture, when we take a look at electrolysis and electrolytic cells, an electrolytic cell is going to be similar to a galvanic cell in the fact that we're going to set it up with electrodes and all of that sort of material. However, electrolytic cells are used to drive a non-spontaneous redox reaction. So when we're getting these E cells that are negative, and we're saying this would be a non-spontaneous redox, an electrolytic cell is a way that we can set that up so that we could drive the non-spontaneous or reverse of what we're expecting here. And when we do that, we're going to need a battery. So we'll need an actual source of electrical current to run through this. So we know that when we have an E cell that is negative, we should use an electrolytic cell if we want this redox reaction to occur. So the way that we would set this up, sort of going with the crude drawing method again, all right, we're going to have a battery. So we can just draw one over here, label this battery. And you can view your battery as a sort of electron pump. So this is going to be the source of electrons or electric current, or how we're really going to do work in this reaction. Okay, and then over here, in this case, we're used to setting up sort of like the two separate half cells for a voltaic cell, but in this case, we can just keep everything in one solution here. So there's going to be two electrodes, and the electrodes are commonly a fairly non-reactive metal when we end up doing these types of electrolytic cell or electrolysis. So you might see platinum, palladium, things of that nature. Okay, and what's key here is that we're going to hook up our battery to these electrodes. Okay, so we've got that wired there. Inside the solution is the reaction that I would like to take place. So this is where the reaction is going to take place. And this is also, you can end up, if you're looking to drive one metal into aqueous form and plate or coat another metal, this is a way that we can do that. So right here, okay, I'm going to label this as cathode. And I'm going to label this one right here as anode. And the way that this works is that when the battery is hooked up, right, the battery is going to start by sending electrons out over to the cathode where the reduction needs to occur. Okay, and then this right here, you're going to have the electrical current moving into the electrode. You can disperse it through the solution, and then it's going to come back up through the anode and go back to the electron pump or your battery. Okay, so this is the general way that we can drive a reaction, but the battery, this is very important here, the battery is going to have the proper voltage in order to drive this reaction forward. So if we take a look at the E cell for a given reaction that's non-spontaneous and we say it's going to be negative X, then that means I'm going to expect that my battery is going to, is going to need to supply a minimum of plus X volts, right? So if the E cell is minus X number of volts, then the battery needs to provide plus X number of volts, and that's a minimum. So it turns out that we usually actually are going to try to do an oversupply of voltage just due to the nature of these redox and non-spontaneous reactions. You don't want to meet them right at the bare minimum. You tend to do a slight over voltage that you provide here. So let's take a look at an actual example, all right, where we would need to drive a non-spontaneous reaction like this. So one example that works well is if you take a look at molten sodium chloride. So molten meaning it's in its liquid form. We obviously normally deal with sodium chloride in a solid salt form. Okay, but you can take molten sodium chloride, and if you provide it with the proper voltage and electrons, you can end up creating sodium in a molten form and chlorine gas in its gaseous form. So let's take a look at how we would set this up and then the actual battery power that we would need behind it. So if we take a look at this, the oxidation, if I were to break this down, I'm going to have sodium plus, and I'd have two of them, and then I would have Cl minus, all right? So if Cl minus is going to Cl2, that means minus is going to neutral. That is a loss of electrons. So I would expect the chlorine is going to be oxidized. So the oxidation here, which again is going to be referring to the anode that I'm expecting, okay, is going to be 2 Cl minus in liquid form, because this is coming from the molten form of this, going over to Cl2, right, with a gain of the 2 electrons, or I'm sorry, the loss of the 2 electrons there. Okay, the gain will be on the reduction side. So the reduction right here, that's going to be the cathode, is going to be, if I turn around and I have the 2 sodium plus in liquid form, molten form, and that's going to go to the 2 sodium liquids. And in this case, it's going to need to gain the 2 electrons, so that should be over on this side. All right, so these are the half reactions here. And if I take a look at them, it's 2 electrons for each, so that would be the total number of electrons being passed around here. So overall, if I take a look after the half reactions, the overall reaction is going to be equal to 2 Na plus molten plus 2 Cl minus molten. That's going to go to 2 molten sodium plus Cl2 gas. All right, so if you take a look and you consult a table, you can find that the half reaction for the Cl2 with the Cl minus is going to be plus 1.3 volts, and then the value for the half cell for the sodium, okay, so let's just mark down here, this is the chlorine, this is the sodium. Okay, this half cell is going to be negative 2.7 volts. So again, the cathode, which is going to come first, was the sodium. So if I want to calculate E cell here, E cell is going to be equal to negative 2.7 volts minus a positive 1.3 volts, which is going to equal approximately 4, or negative 4, I should say. That's a big difference there. Negative 4 volts. Okay, so this is certainly not going to be a spontaneous cell as far as driving the redox. So if I pick up a battery, I'm going to need a battery, okay, that must have at least plus 4 volts. That's a minimum requirement. And again, I'd like a little bit of overvoltage, so you'd probably want one that has a ranking slightly higher than that. All right, now one of the things that you can utilize when you're starting to do this chemistry is you can use charge in order to predict the amount of product formation. So if a battery is giving out a certain amount of charge over time, you can use Faraday's constant and the rating on the battery in order to predict approximately how much material you're going to end up creating on a mole or a gram level. Okay, so this is essentially using charge to predict product formation. And electrolytic cells, when we work with them, they are going to use a current, right? So the battery is going to have a current which is normally rated in amperes or amps, and it's also going to be applied for a certain amount of time. So when we turn the battery on, there's a certain amount of time in seconds that the battery uses, okay, or is used, and then I turn it off. So we can define a coulomb, which is a charge for an electron, okay, as equal to 1 amp times 1 second. So if I know the amp that's being provided by the battery, and I know how long I intend to run the battery for my electrolytic cell, then I can end up creating a situation where I can then find the moles of electrons that are going to be passed through a certain time. So I can use Coulomb's and Faraday's constant in order to find the moles of electrons, and if I know the moles of electrons, I can relate that through the redox reaction back to the moles of compound, the actual, whatever it might be, if it's magnesium, silver, copper, whatever I'm working with. So let's take a look at another example here, another molten example. Okay, so in this time, instead of sodium chloride, we're going to go ahead and say, let's do calcium chloride. So calcium chloride in a liquid format, that should be Cl2 there. Let's rework that so it looks nice. Cl2. Okay, so molten calcium chloride is going to go over to calcium in its molten form plus the Cl2 in its gas form. Okay, another very common electrolytic reaction is going to be water going to hydrogen gas and oxygen gas. So you'll see that very often. Okay, so the anode, where the oxidation is occurring here, the anode is going to be the Cl once again. So it'll be 2Cl minus in its liquid form. And that is going to go to the Cl2 gas plus 2 electrons. And then we also have our cathode. So for the cathode, in this time it's calcium. We're going to have calcium 2 plus in a liquid form. And that's going to go to, wait a minute, let's make sure we put the electrons in there. 2 electrons, because it's a 2 plus. And that's going to go to the molten calcium. All right, so now we know the anode and the cathode, if we're looking at this. And here's how we're going to set this up. All right, you're going to have to find the coulombs first. So in this reaction, we're going to provide ourselves with a battery. And the battery is going to have a rating of 0.452 amps. Okay, and we're going to use it for, let's say, an hour and a half, 1.5 hours. Okay. So there's going to be a couple conversions we have to do here. First of all, we need to find the coulombs. So the coulombs are going to be equal to the amp rating, so 0.452 amp, okay, times the seconds. Now we're told hours here, so we're going to have to convert that. So 1.5 hours is going to equal 3,600 seconds, right? So it's 60 and 60, so you get 3,600, right, in every 1 hour. 60 meaning minutes, so 60 seconds to a minute, 60 minutes to an hour. Okay, and then that is 1 coulomb per 1 ampere second. So if you go through and you look at all of this, all right, you're going to cancel out your hours, you're going to cancel out the seconds and the amps, so you're just going to end up with the coulomb here, which is what you're looking for. All right, so if we solve for this, we end up finding a value of 2.44 times 10 to the third coulombs. So this is essentially a way of telling us how much charge is being passed through the electrolytic cell as we're trying to drive this reaction. All right. So if I would like to find out how much of each is formed, I can utilize this value here now. So let's say, first of all, how much of the molten calcium was formed. Well, to do that, I'm going to take the value. So the value was 2.44 times 10 to the third coulombs. Okay. I can multiply that by Faraday's constant. Now, I want it to cancel out in terms of the coulombs, so it's going to be every 1 mole of electrons is going to be 96,500 coulombs. So now the coulombs are gone. All right, now I need to get this into the actual equation here. So I'm going to want the moles of calcium per the moles of electrons. Okay. So we have to look how many electrons were actually transferred here for a mole of calcium. Well, 1 mole of calcium, based on this equation here, has 2 electrons being passed back and forth. Okay, so for every 2 moles of electrons, I'm going to get 1 of my molten calciums. And then the last thing I need is the molar mass for calcium. So this would get me the moles, and if I wanted to know the grams, I would take it one step further and I could say it is 40.08 grams of calcium in every 1 mole of calcium. So what I end up with in a situation like that, if I put all that together, is 0.507 grams of calcium. So by just knowing the redox I'm interested in and how long I'm going to be passing a current over that redox electrolytic cell, I can predict how much of the calcium I could generate in a case like that. All right. So now let's do the same thing for the chlorine. So let's say I'd like to know how much of the chlorine gas is going to be produced. So I'm going to start on a similar path. It's going to be 2.44 times 10 to the 3rd coulombs. Faraday's constant isn't going to change, so it'll be 1 mole of electrons for every 96,500 coulombs. Those are gone, right? And then I'm going to say times. Now, if I look at the equation, it's 1 mole of Cl2, and the mole of Cl2, it's the same electrons being passed back and forth. That's 2 electrons, right? So here's the 1 Cl2, an implied 1 there, and here's the 2 electrons. All right, so 1 mole of Cl2 for every 2 moles of electrons, and it is important you're referencing the stoichiometric coefficients there. Okay, now what is the mass for the chlorine? It's diatomic. It would be 70.90 grams of Cl2 in every mole of Cl2. Right, so moles cancel, and then if I solve for that, I'm going to end up with 0.896 grams of Cl2 that is produced. All right, so that's going to wrap up the electrolytic cells and electrochemistry when we're trying to drive these non-spontaneous reactions. So again, the biggest key here is in a voltaic cell, you're actually going to generate some useful voltage or current through the natural spontaneous redox reaction. Here, we're trying to drive the opposite using a battery. Now, this can be useful. What happens if you want to create molten sodium, right, and you can cool it down and work with regular sodium or whatever it might be? Sodium is very difficult to obtain in its natural form, right? You have to drive some sort of non-spontaneous process in order to get just elemental sodium. So this has its purpose and its use because some non-spontaneous reactions may be of interest to us as chemists or people in the world. So that's where I'm going to leave this lecture.